This video is going to introduce the word percentile. Here's the outline of how the video is going to go. I'm going to remind you that in other contexts, other software, other environments, you might see the word quantile used in place of the word percentile. Now, there's technically a distinction to be had here whether or not you're going to write out a percentage, like 50%, or you're going to write it out as 0.5. R uses by default the word quantile, but as long as you remember, they're basically just synonyms. Everything should be all right. I'll remind you that probability is area under a density function. I'll give you a definition. It's going to be, let's have the definition show up both in pictures, symbols, and words. And then past that, we'll dive in to do an example in R, where I'll try to keep the population side, which is to represent percentiles as new population parameters, in one chunk of code, and then in a separate chunk of code, I'll show you the sample side, how we can estimate percentiles as population parameters. So here we go. The running example is going to be for a normal distribution with mean equal to 1,000 and variance equals to 250 squared. Now for this example, you can imagine this distribution represents SAT scores, where the mean SAT score is 1,000 and the standard deviation of the SAT scores is 250. I certainly made up these numbers, but I think they'll give you a reasonable understanding of what percentiles are after in this context. So here we go. Let's draw as best a normal distribution as I can, and then brag about how good that is. That's not bad. Here, this distribution is going to be centered at 1,000. And I like to write the standard deviation just kind of hovering in the top right corner. Okay, so we're going to use this to provide a context in which we remember that probabilities show up as areas under the curve. So if I wanted to look at area in the left tail, maybe I'd say there's, I don't know, let's pick 30% underneath the curve in the shaded area, and that would be a 30% as a probability. And recall that all the area under the curve is going to integrate to 1. Okay, so there's our quick reminder that probability exists as area under curves. Let's move on to a definition of a percentile. Now, the definition actually shows up as a picture by defining that point, pi subscript 30, that point that which 30% of the SAT takers is less than that value. Now, percentiles are always defined as less than the value, putting such a percentage of area under the curve. So here we have the percentile pi subscript 30, whatever SAT score that is, that puts 30% to the left of that number, is the 30th percentile. So we have for p in 0 to 1 for some probability, the 30th, let's generalize this, the p times 100th percentile is the number pi subscript p, I guess we'll write a decimal, pi subscript p times 100. That puts pi times 100% of the area to the left of pi subscript p. So the definition of in words is really not that helpful. I think the picture acts as a much better guide for what this thing is doing. Similarly, we could write this out in symbols by saying P is the value equal to the probability from your random variable less than pi subscript p. If you wanted to think of that as an integral under this continuous distribution, you could say we're going to integrate from all the way off to the left up to the value pi sub p times 100. That puts area under the density function f up to that point, pi subscript p times 100, equal to the value p of interest. Okay. Let's dive into R and see if we can convince R to draw us some very similar pictures where we'll keep this example of the normal distribution with mean equal to 1,000. That's like a mean SAT score of 1,000 and a standard deviation equal to 250. Okay, I'm gonna draw pictures in R, so I'll load the library ggplot. And now we're gonna work on the population side, where the mean is equal to 1,000 and the variance is 250 squared. With these two numbers, we could calculate pi sub 30 to be Q for quantile in R, norm, since we're working with the normal distribution, and we want the 30th percentile corresponding to 0.3 area to the left of the number that this function will return, with a mean of E and a standard deviation of the square root of V. I will wrap this expression in some extra parentheses to force it to print at the same time. So here, pi subscript 30 is equal to the SAT score 868.9. The SAT score 868.9 puts 30% of SAT takers below that score. If we wanted to draw this in a picture, we could, using the rules we established in a previous video, pick out bounds for a plot to represent the support of this continuous distribution. Where we recall, since we're on the population side, we can pretend like we know the density function for the population to have mean E, 1,000, and standard deviation, the square root of V, or 250. Let's run all these to make sure there's no errors. Then using our function ggplot from the library, ggplot2, we could draw the density function that represents the SAT scores with a mean of 1,000 and a standard deviation of 250. Now, to add a vertical line at the x-intercept equal to pi 30, we could represent that score, which is 868.9, on the plot by this vertical line. And 868.9, the 30th percentile, is that value on the x-axis, such that there's 30% of the area under that curve to the left of the vertical line. This is the population side discussion of a percentile. Feel free to change pi 30 to, well, really that's just the variable name I chose, but if you want to calculate a percentile or quantile from a normal distribution with some mean and some standard deviation, you could plug in whatever percentage as a decimal place you wanted into the first argument of the function named Q norm. If, on the other hand, we wanted to consider the sample side of things, such that all we had was a vector of randomly generated normal data, let's say 314 observations with a mean of E and a standard deviation of 250, then we could estimate pi 30, maybe by calculating pi hat 30, by calculating the quantile of x corresponding to the 30th percentile. And again, I will wrap this expression in parentheses so it stores and prints at the same time. And here we have pi hat, a guess of pi 30, to be 840, which I will reprint pi 30 to show you is an okay guess for the true population parameter, the 30th percentile of 868.9. 840 is a reasonable guess of 868.9. And similarly, like we've seen before, if you just increase your sample size and guess again, you will be closer to the true population parameter. Now, if you just want to check out what this would all look like on the sample side, we could similarly estimate all of these population parameters using our sample of, now with the increased sample size, we have 31,400 observations, estimating pi 30 with the estimate pi hat 30. We put all that into a data frame and recreate this plot we have on the bottom right from a finite sample. You can see it's a little bit more squiggly. It's not as perfectly smooth since we are now on the sample side, but we're estimating the population parameters, the density function, and the 30th percentile quite well.